Hello everyone, I'm Sabin Thapa, a PhD physics student, and today I'll be discussing quarkonia, probing the Big Bang on Earth. My advisors are Dr. Ramona Vogt and Dr. Andrew Hanlon. Here's an outline of what we'll cover in this video. We'll start with an introduction and motivation, then discuss matter at different physical conditions, including heavy ion collisions, and finally, look at quarkonia as a probe for the quark-gluon plasma. Let's begin by considering what happens when we heat or pressurize matter. As you can see with water, changing temperature and pressure leads to different states like solid, liquid, boiling, and gas, as shown in the phase diagram. So what are we made of? Everything around us, and indeed ourselves, are composed of elements found on the periodic table. But what's inside the atom? Through various experiments like J.J. Thomson's plum pudding model, Rutherford's gold foil experiment, and Chadwick's discovery of neutrons, we've learned about the subatomic structure, revealing a dense nucleus surrounded by electrons. What if we zoom in even further? At very high electron energies, protons and neutrons reveal their substructure, showing the existence of quarks and gluons. These are the fundamental constituents of matter, as described by the Standard Model. They include 3 generations of quarks and leptons, along with force-carrying bosons like gluons and photons. Quarks and gluons combine to form hadrons, such as protons, neutrons, and mesons. This confinement is due to the strong nuclear force, which is incredibly powerful at larger distances. What about matter at extreme conditions? When matter reaches incredibly high temperatures, around 10 to the power of 12 Kelvin, it transitions from a color-confined state, where quarks are bound in hadrons, to a deconfined quark-gluon plasma. This diagram illustrates the different quantum chromodynamics, or QCD, phases of matter. It shows how temperature and baryon density affect the state of matter, transitioning from hadronic matter to a quark-gluon plasma. So where and why do we study quark-gluon plasma? It was formed microseconds after the Big Bang, providing a unique glimpse into the early universe. Scientists like Robert W. Wilson and Arno Penzias discovered the cosmic microwave background, evidence of this early universe. We can recreate Big Bang conditions here on Earth using powerful colliders like the Large Hadron Collider at CERN and the Relativistic Heavy Ion Collider at Brookhaven National Lab. These relativistic heavy ion collisions create mini Big Bangs, producing conditions similar to the early universe. We study both soft probes and hard probes to understand the quark-gluon plasma. Quarkonia are key probes for the quark-gluon plasma. They are mesons, which are bound states of a heavy quark and its antiquark. Carbonium and bottomonium are examples with different masses. Experimental observations of quarkonia in heavy ion collisions show distinct signals. These plots illustrate the measured yields in different collision systems, which help us understand the behavior of quarkonia in the quark-gluon plasma. Quarkonia act as a quark-gluon plasma thermometer. The phenomenon of static screening, where color charges are screened within the QGP, leads to the sequential melting of different quarkonia states at high temperatures. Now let's consider how we model quarkonia in the quark-gluon plasma. This image provides a conceptual representation of a quarkonium moving through the plasma. If a quarkonium were a classical object, its motion would be described by Newton's laws, much like a basketball being thrown, where force equals mass times acceleration. However, quarkonia are quantum objects. Their behavior is governed by quantum mechanics, specifically the Schrödinger equation, which describes how quantum states evolve over time. We use the theory of open quantum systems and effective field theories to study the quantum transport of quarkonia within the QGP. The goal is to understand their dynamics in this extreme environment. Other dynamic effects are crucial in the QGP. High-energy plasma particles can collide with quarkonium-bound states, reducing their lifetimes through dynamical screening and promoting regeneration. The evolution of the bottomonium density matrix in the QGP within the Markovian limit is described by a quantum master equation. Jump operators within this equation encode the effects of the QGP, allowing transitions between quantum states. To quantify the modification of quarkonium properties, we use the nuclear modification factor. This factor compares the yield of quarkonia in heavy ion collisions to a proton-proton baseline. These plots showcase some of our theoretical results and predictions, which are crucial for understanding quarkonia behavior in the quark-gluon plasma. In summary, ordinary matter's true colors are hidden, with quarks and gluons confined in hadrons. We can momentarily melt this confinement in colliders, recreating the Big Bang's primordial soup. Thank you for watching. These are the main features of quantum chromodynamics: asymptotic freedom, where the interaction strength decreases at short distances, and color confinement, which means quarks always form colorless bound states called hadrons.